In this video we discover affine transformations. As always, we will go straight to the areas we need for later topics. So this video leaves out some details about affine transformation but covers the most important. Affine transformations allow us to elegantly transform vectors for computer graphics or collision detection, for example. Hi, my name is Alex and this is another video in the series about math for coding with vectors. So far we looked at basis vectors and its matrices in a rather static way, where the basis stayed at the origin. There we only allowed it to rotate. What we would like to add is a translation so the frame can move freely in space. For example, let's say we have our frame M here and we would like to add a translation to it like so. Our familiar equation would add that translation t right to the end. But we could actually do better than that by having a matrix carry the translation, so we end up with only one elegant matrix operation. So let us dissect the transformation. Writing out the whole equation, we see that the translation t simply adds to the scalar product at the end of the equation. In the previous video we already had a similar situation where we constructed an augmented vector for the normal equation of the line. We can do the exact same in this situation. We can augment the transformation matrix M with a translation t by adding it to the end of the matrix as an additional column vector. Every point we would like to transform by that basis, we simply need to augment that vector with a 1 at the end. This is called an affine transformation. Performing matrix-matrix operations do not change. We can still combine matrices the way we already know. For example, we can construct a transformation by translate and rotate, or by rotate and translate. Here R is our rotation basis and T is a translation matrix we will explain in a moment. Note that if we perform an inverse operation of matrix M, the matrices led to M change place. For example, inverting the matrix RT will result in a matrix inverse T times a matrix transposed R. Now let's look more closely to what those matrices are. Since we augmented the vectors with a 1, we need to add another row at the end of every matrix so that matrix multiplication is possible. The matrix RT consists of a matrix R with an additional augmented column and row vector at the end. The translation matrix T includes a 2x2 identity matrix I in the upper left corner with a translation inserted on the right as the augmented column vector. If forward transformation 1 is computed, we end up with a matrix that holds the R in the upper left and the rotated translation T in the upper right corner. In this transformation, the translation is performed first, so that translation is rotated by the second matrix multiplication with R. We look at this more closely in the next chapter. The inverse of transformation 1 performs the opposite transformation. First it rotates, then it translates in the opposite direction by performing a backwards translation with -t. We can do the other way around also. First rotating and then translating. The resulting matrix does exactly that. As we can see in the upper right corner, the translation t stands alone. So this means the translation is performed individually and then the basis is rotated. The inverse of that is quite different. Interestingly, the reverse operation rotates the translation and performs a rotation afterwards. We saw how to transform the basis matrices. Now let's look how this is acting on vectors. In math with column vectors, we read a chain of operations from the right to the left. So vector v is transformed by applying matrices from the left. In this example, the vector v is first translated and then rotated. In the inverse case, a vector w is first rotated in the opposite direction and then translated back. It is just that simple. Here we look at some common affine transformation matrices. A rotation matrix is constructed by putting our own basis vectors into the upper 2x2 array. Note that EX and EY are 2D vectors. In the inverse case, the column vectors change to row vectors. Please remember that the inverse of an orthonormal matrix is always its transpose. The translation matrix is very simple. We simply put the translation at the end as the augmented column. The inverse of that is a negative translation that can be written in the exact same way, except that we write the negative translation. The affine transformation also includes scaling of spaces. So a scaling matrix puts its coefficients in the main diagonal. The inverse does the opposite. It divides the space by the coefficients, which are placed in the main diagonal. All these operations can be chained together as we see fit. Finally, let's look at an example. The matrix M first rotates the vector v and then translates it. It ends up being vector w. The inverse performs the opposite operation. It first translates the vector w by -t, and then it rotates the difference vector in order to become the local v again. In this video we learned about affine transformations. In the next videos we will use all of the topics out of the series about vector math and do collision detection on various primitives. Until next time, stay safe, bye now.